Hi, in this video we are going to discuss about partitioning and placement in FPGA. നമ്മുടെ module 4 FPGA based system design S5 honors module 4 topic ആണ് partitioning and placement. Over to the topic. Now before going to the topic, let us refresh the FPGA architecture part. An FPGA architecture consists of three main parts. They are the CLBs, or configurable logic blocks, that are in blue boxes. Then we have the IO cells, or IO blocks, input output blocks, which are marked as yellow. And then we have the interconnects, or the so-called routing resources. The logic modules are can be, or the configurable logic blocks are actually consisting of the combinational and sequential circuits that we implement, or the design of logic functions that we are going to implement. And then we have the routing resources, that are prefabricated wire segments, uh, which consist of programmable switches. And then we have the IO blocks, or input output cells. Now, this is how you have the structure of a classical FPGA. Now, coming to the basic elements of a CLB, or configurable logic block. You can see a configurable logic block, or CLB, consists of a flip-flop, lookup table, and multiplexers. The flip-flop stores the state information of a circuit, while lookup table is actually a table that contains that generates the output based on the inputs given. You can see a simple example of a lookup table with two inputs A and B, and you get an output C based on this table. So it is like a lookup table is a table that generates output, and these values are stored in small RAM. And like here you have A and B, they are the address pins, and C, or output, is a data pin. Every time your address pins are changing, they are pointing at a different address entry, and they are reading out the result, which is 0 or 1, that is based on the inputs that are given. Now coming to the FPGA design flow, FPGA CAD flow, that is the FPGA computer aided design flow, in which you have the various steps that we already dealt with in the design flow, or of FPGA. Here you have the basic steps, like the first part is HDL, or schematic, and the HDL coding, and then we continue with the syntax checking and simulation. And then what happens is we go to the logic synthesis part. It is followed by the actual physical design, that is the placing and routing of the FPGA. And once placing and routing is done, you generate the bit stream of the corresponding program, which is dumped into the FPGA. So the two main physical design steps are place and route. So what is placement? Placement is the process of placing the cells, or searching the appropriate location within the chip floor for each cell in the netlist. Place and route describes the processes where the netlist elements are physically placed and mapped to the FPGA physical resources. About this place and route technique, in which you place all the elements based on our rules in the placing and routing step, and then they are mapped to the FPGA physical resources. It takes only a few seconds for a small FPGA, but it may take many hours for a bigger one. The place and route software, that is done based on particular algorithm, and it is always done by FPGA software that is given by that is from the FPGA vendor. You know what, FPGA vendors that normally they do not uh, give the information, more information about that, about the internal things in the chip. So it's all what they create and the vendors create based on their software. And after synthesis of placing and routing, you have after those synthesis and every steps, the last part will be the generation of bit stream to dump into the FPGA. Now, based on the design implementation, I told you about the three steps, that is partitioning, placement, and routing. In partitioning, it is breaking up the design to fit into the different configurable logic blocks. And these log blocks, of course, has some LUTs and flip-flops. Based on that, we will break the design further. Now, placement is choosing the right CLB based on the proximity to IO blocks, input-output blocks. IO ബ്ലോക്സിന്റെ ആ ഒരു കണക്ഷൻസ് മാക്സിമം ഡിലേ കുറച്ചുകൊണ്ട് തന്നെ വയേഴ്സ് ഏറ്റവും കുറവാക്കിക്കൊണ്ട് തന്നെ എങ്ങനെ നമുക്ക് ആ പ്ലേസ്മെന്റ് അല്ലെങ്കിൽ CLB ചൂസ് ചെയ്യാം എന്നുള്ളതൊക്കെ ഇറ്റ്സ് ഓൾ എ പാർട്ട് ഓഫ് പ്ലേസ്മെന്റ്. And coming to routing, we have the routing process in which we chose the interconnects based on the timing constraints and all area constraints, everything, and the chip density. It's all based on this routing too. Coming to circuit compilation, you can see ഞാൻ തൊട്ട് നേരത്തെ പറഞ്ഞ പോലെ തന്നെ partitioning, placement and routing എന്ന് പറഞ്ഞ മൂന്ന് സ്റ്റെപ്സ് കാണാം. It is partitioning in which നമുക്കുള്ള ആ ഒരു സർക്യൂട്ടിന്റെ you have the input and outputs, right? Based on that, you design a lookup table with so many inputs and the output as required. Lookup tables are designed, and such lookup tables are assigned to various logic blocks. That is called placement. For partitioning, we or technology mapping in which we develop the lookup tables and all things, flip-flops, everything. And after this, the next part is assigning these lookup tables and elements to the various configurable logic blocks. It's called placement. പ്ലേസ്മെന്റ് കഴിഞ്ഞിട്ട് പിന്നെയുള്ള സ്റ്റെപ്പാണ് റൂട്ടിംഗ്. അപ്പൊ നമ്മൾ വി വിൽ ചൂസ് എ ഫ്യൂ ലോജിക് ബ്ലോക്സ് അല്ലെ. അപ്പൊ ആ ലോജിക് ബ്ലോക്സ് എങ്ങനെ കണക്ട് ചെയ്യണം എന്നുള്ള ആ ഒരു റൂട്ടിംഗ് പ്രോസസ് ഇസ് ഷോൺ ഇൻ ദ നെക്സ്റ്റ് ഫിഗർ. This is the routing process. You can see how they are connected and how they are interconnected. The wire segments and switches, all things are represented in routing, are done in routing. Now, further programmable interconnections are done after that. We already have done the configurable logic blocks. And then what we do the further interconnections or routing process, and we finish the design. Now, this is an example of placement and routing. There is silence. Now, what happens here is we fully design the circuit, and completely merged circuit is translated into a special format that is understood by silence computer aided design tools. This format is called XNF. അപ്പോൾ .xnf എന്ന് പറഞ്ഞ ഒരു സൈലൻസ് നെറ്റ്ലിസ്റ്റ് ഫോർമാറ്റിലേക്ക് നമ്മളത് കൺവേർട്ട് ചെയ്യും. അപ്പോൾ ഈ XNF സർക്യൂട്ട് എന്ന് പറയുന്നത് ഈ നമ്മൾ പാർട്ടീഷൻ കഴിയുമ്പം കിട്ടുന്നതാണ്. ഇറ്റ് ഇസ് കോൾഡ് ടെക്നോളജി മാപ്പിംഗ്. ടെക്നോളജി മാപ്പിംഗിൽ ഇറ്റ് കൺവേർട്സ് ദ XNF സർക്യൂട്ട് into a netlist of silence logic cells. The logic cells used depends on which silence product the circuit is implemented in. But the mapping procedure, mapping അനുസരിച്ച് it is either to minimize the total number of logic cells required or the number of stages of logic cells in the circuit. Now, coming into detail about FPGA placement. So your topic really starts from here. That was just an introduction of the placement process. Placement is the process of finding a suitable physical location for each cell in the block. Earlier, I was telling you about the partitioning part also. Placement and routing is an interconnecting stage in design of PCBs. And it is a process where all these electronic components, this logic gates, everything is accommodated in that limited amount of space. But the following, then no, you have the routing process. Placement is simply it's not just a place um, where all these can be accommodated. Other synthesized netlist item it is available that is needed to optimize the design. About area constraints, timing constraints, the delay constraints, all should be considered and all should be optimized to get a better placement. അപ്പോൾ poor placement ആണെങ്കിൽ അവിടുത്തെ പ്രശ്നം എന്തായിരിക്കും? അവിടെ പെർഫോമൻസ് ഡിഗ്രഡേഷൻ ഉണ്ടാവാം, ഡിലേ ഡിലേ കൂടാം, ടൈമിങ്ങിന് പ്രശ്നം വരാം. So many disadvantages. അപ്പോൾ now what are the objectives of a good placement in FPGA? So we have a few points. One is minimize the required wiring. അപ്പോൾ ആ ഒരു വയർ ലെങ്ത് ഡ്രിവൺ പ്ലേസ്മെന്റ് ആണ് നമ്മൾ നോക്കേണ്ടത്. ഇൻ ഓർഡർ ടു അവോയ്ഡ് കൺജഷൻ എല്ലാം വളരെ കറക്റ്റ് ആയിട്ടും നല്ല കോമ്പാക്റ്റ് ആയിട്ടും ഉള്ള വയറിംഗ് നമ്മൾ ചൂസ് ചെയ്യണം. വയറിങ്ങിനനുസരിച്ചുള്ള പ്ലേസ്മെന്റ് ചൂസ് ചെയ്യണം. ബാലൻസ് ദ വയറിംഗ് ഡെൻസിറ്റി അക്രോസ് ദ FPGA. ആൻഡ് ദെൻ അപ്പോൾ നമ്മൾ IO ബ്ലോക്സിനടുത്ത് ഏത് CLB ഏത് സർക്യൂട്ട് വേണം അങ്ങനെയുള്ള കാര്യങ്ങളൊക്കെ ഇറ്റ് ഈസ് കൺസിഡേർഡ് ഹിയർ. Now next is maximize the circuit speed. അപ്പോൾ നമ്മുടെ ആ പ്ലേസ്മെന്റ് അനുസരിച്ചായിരിക്കും സർക്യൂട്ട് സ്പീഡ് കൂടുന്നത്. അപ്പോൾ ലോങ്ങർ വയേഴ്സ് വെച്ചാൽ ഡിലേ കൂടും, ടൈമിംഗ് കൂടും അല്ലേ? അപ്പോൾ അതനുസരിച്ച് വേണം നമ്മുടെ സർക്യൂട്ട് സ്പീഡും ഇംപ്രൂവ് ചെയ്യുന്ന രീതിയിലുള്ള പ്ലേസ്മെന്റ് വെക്കണം. ആൻഡ് ദെൻ മിനിമൈസ് ദ പവർ ഡെസിപ്പേഷൻ ആൻഡ് ഓൾസോ മിനിമൈസ് ദ ക്രോസ് ടോക്ക് ബിറ്റ്വീൻ സിഗ്നൽസ് ആൻഡ് നെറ്റ് ഡിലേസ്. So these are the objectives of placement in FPGA. നല്ല പ്ലേസ്മെന്റിനാണെങ്കിൽ we should have consider these things. So this is just an example of good placement and bad placement. This is an example of good placement and this is an example of bad placement. You can simply look into the figure and understand what is the difference. അപ്പോൾ ഇതിനകത്ത് പ്ലേസ്മെന്റ് കറക്റ്റ് അല്ലാത്തത് കൊണ്ടാണ് so much of wires extra വേണ്ടി വരുന്നത്. Right. You can just go through this figure. അതിനകത്ത് ഇതെങ്ങനെ മാറ്റിയിരുന്നെങ്കിൽ നിങ്ങൾക്ക് നല്ലൊരു പ്ലേസ്മെന്റ് കിട്ടുമായിരുന്നു എന്നുള്ളത് ഇറ്റ്സ് ജസ്റ്റ് ലൈക്ക് ജിക്സോ പസിൽ നിങ്ങൾക്ക് തന്നെ ഒന്ന് ആലോചിച്ച് നോക്കാവുന്നതേ ഉള്ളൂ. Now the placement algorithms can be classified into three major categories. One, partition based method like min cut partitioning, simulated annealing method and analytical placement method. These are the three main methods. Now coming to each one of them. A partitioning based method on min cut partitioning. But the given circuit is repeatedly partitioned. അപ്പോൾ ഈ ഒരു മെത്തേഡിൽ എങ്ങനെയാണെന്ന് വെച്ചാൽ the given circuit is partitioned. അപ്പോൾ നമ്മൾ ഈ ടോപ്പിക്കിൽ we come into the partitioning process. Partitioning ആണ് ഇനി പറയുന്നത് in which the first thing is we partition the circuit, the whole circuit into different sub-circuits. അപ്പോൾ അങ്ങനെ ചിപ്പ് ഏരിയ is partitioned accordingly. അങ്ങനെ വെർട്ടിക്കൽ ആയിട്ടും ഹൊറിസോണ്ടൽ ആയിട്ടുള്ള സബ്സെക്ഷൻസ് ആയിട്ട് നമ്മൾ ഹോൾ ചിപ്പിനെ നമ്മൾ ഡിവൈഡ് ചെയ്യുന്നു ആൻഡ് ദെൻ സെഗ്മെന്റ് ചെയ്യുന്നു ആൻഡ് ദെൻ each subcircuit is assigned to a subsection. The process is repeated until each subcircuit consists of a single logic block. അപ്പോൾ അതങ്ങനെ ഒരു യൂണിക് ലൊക്കേഷൻ ഓൺ ദ ഷിപ്പ് ഏരിയയിൽ നമുക്ക് കിട്ടുന്ന പോലെ വി കീപ് ഓൺ റിപ്പീറ്റിംഗ് ദ പ്രോസസ് ഓഫ് പാർട്ടീഷനിങ്. അപ്പോൾ പാർട്ടീഷൻ ചെയ്യുമ്പം ദ നമ്പർ ഓഫ് നെറ്റ്സ് ദാറ്റ് ആർ cut by partitioning is usually minimized. Now coming to the partition algorithms, there are mainly two types of partition algorithms that are being used. The earlier type was a simple greedy algorithm. A simple greedy algorithm, as the name itself, it accepts only moves with immediate benefit. Normally it leads to a problem in which it leads to local minimum from which the algorithm cannot escape. Loop pole aipo. So in order to avoid this, we have the new proposed method, that is KL algorithm or Kernighan and Lean approach for graph bisectioning algorithm. ഇതിനകത്താണെങ്കിൽ what they do is this is an iterative process in which pairwise swapping of vertices is done. It is done until no improvement is possible. The first type of min-cut algorithm is a rain-cut algorithm, in which you have the whole chip is partitioned into two blocks, and then divide the circuit into sub-circuits to reduce the net cut. A partition all the blocks intersected by the first of all just divide into two blocks A and B, and then again further divide into smaller blocks. Now then the partition can be continued until the blocks A and B are generated, and further uh, blocks like first divide this into C1, then you have this C2 bisecting lines followed by C4. Next type is block-oriented min-cut placement algorithm, in which you have the whole chip that is divided into two main regions. So for each region, we choose separate cut line and partition the region further. Other than that, we have this partitioning, in which one part becomes B1 and the other part will be B2. ഇങ്ങനെ partition ചെയ്തു കഴിഞ്ഞാൽ the first part will be B1. This all portions become B1, and the other part forms B2. Again, this B1 and B2 are further partition not to obtain B22, and here to the left side you have B11, B1112, B121, and B122. Similarly, in to the right side you have B211, then B2112, B212, B2211, and B2221. Quadrature placement procedure is like you have four partitions. One, just like you have the first main partition, which is shown as line 1. The second main partition, that is given mentioned as number 2. And then we have two further bisections like 3A and 3B. That is followed by 4A vertical bisections, 4A and 4B. Coming to the bisection placement procedure, in which again you have the first one line, that is 1. Then we have two further bisections like 2A and 2B, equal lines. Then we have the next divisions, which are again dividing this 2A portion into 3A, 3A and 3B. And here you have 3C and 3D. So after finishing this, we again divide the placement into further bisections like 5A, 5B, and for the division 6A, 6B, 6C, and 6D. These are the different types of bisection placement procedure. That is, each row is bisected again and again until its subregion has just one space. This is another method, the slice bisection procedure, in which again rows are sliced by horizontal cut lines. First of all, we have all the row slicing, and when the rows are done, we go for vertical cut lines 8, 9, 10. So we discussed about the different types of min-cut partitioning algorithms, and the second type of uh, partitioning is the simulator annealing, in which the name comes from heating and cooling metal to increase the size and quality of crystals to make it harder and stronger. POE or concept is being used in simulated annealing, and it finds the best placement at low cost. That is, it searches a configuration with low cost by iteratively moving the current configuration to a neighbor configuration. അപ്പം ഒരു ജിഗ്സോ puzzle പോലെ continues to uh, move the current configuration to a neighbor configuration, uh, and the movement is accepted if the current configuration has an advantage of lower cost. So simulated annealing method, that such kind of algorithms are comparatively slow, just like solving a jigsaw puzzle. It especially so just like what you see in the figure, we start from the initial placement or random position, and then keep on changing by kind of block exchanging or swapping, such that the if the blocks are exchanged and it results in lower cost, then that movement is accepted. It is accepted until the change in cost is less than zero, or even else that swapping or simulated annealing process can be accepted if cost increase is not too much. Just like solving a jigsaw puzzle, you start from the random or initial position, and then go for the uh, different moves so that um, an optimum cost is achieved. So this simulated annealing based placement algorithm was popularly used in the mid 1980s. It was by Timberwolf Place and Root Package. ഇതിനകത്ത് പറയുന്നത് എന്താണെന്ന് വെച്ചിട്ട് it has this placement algorithm is of two parts. while stage 1 and stage 2 ആയിട്ട് to each side. Stage 1 it allows overlaps among cells and movement of cells between rows. Row-wise movement of swapping is possible. And the second stage, in which it eliminates all overlaps and only performs the interchange of adjacent cells. അപ്പോൾ ആ ഒരു രണ്ട് സ്റ്റേജ് വഴിയാണ് have the simulated annealing process. അപ്പം it then finally results in optimum cost. The analytical method and a third method, that is the numerical method to compute the coordinates. It is often based on quadratic wire length objective. The wire length is minimized using the numerical technique. Now, three stages of FPGA placement that is also important. അപ്പോൾ മൂന്ന് സ്റ്റേജ് ആയിട്ടാണ് FPGA പ്ലേസ്മെന്റ് നമ്മൾ ഡിവൈഡ് ചെയ്തിരിക്കുന്നത്. One is global placement, legalization and detail placement. Global position എന്ന് പറഞ്ഞാൽ global placement എന്ന് പറഞ്ഞാൽ we compute the best position for each module to minimize the cosmetics or to avoid the non-overlapping constraint. അപ്പോൾ ഗ്ലോബൽ പ്ലേസ്മെന്റ് ഒരു ഇനീഷ്യൽ ആയിട്ടുള്ള ഒരു പൊസിഷനിങ് പ്രോസസ്സ് വേഗമായിട്ടൊന്ന് ചെയ്യാൻ വേണ്ടിയിട്ടാണ് ആ ഗ്ലോബൽ പ്ലേസ്മെന്റ് computation. Second type is legalization that removes the overlaps and places the modules into their corresponding sites to minimize the displacement for global placement. And the last stage is detailed placement, in which it further refines the solution quality by making even more better placement or position of different modules. Coming to the FPGA specific placement issues, main placement issues include the number of routing tracks in routing channels, which is normally fixed on an FPGA. The second issue is regarding uh, the condition for any feasible placement, that is the channel density. So the channel density in every channel cannot exceed the number of routing tracks available. First thing is routing channels and channel density. The second problem is, in order to calculate the channel density, some simulated annealing placement algorithms and also global routing can be iteratively done. An FPGA contains routing tracks of various lengths. Simple interconnection delay estimation model based on net length or are not accurate enough for use in FPGA algorithms. Fast and accurate interconnection delay computation methods are needed for timing driven FPGA placement. So these are a few issues of placement in FPGA.